The element sulfur is a yellow solid that has been found naturally in hot water springs. Crystals, which really means just solid, of sulfur formed at these springs consists of lattices made up of S8 molecules. What type of bond occurs inside the S8 molecule? So it's just an SS bond, which is between two nonmetals. They have the same electronegativity, so it's non-polar covalent. Briefly describe the chemical bond named in 1.1. They want you to describe the bond. They don't want to say what's the electronegativity to get to the bond. I gave you marks, but actually what you had to say was it is the even sharing of electrons between two atoms or something like that. What type of intermolecular forces occur between S8 molecules? So I've got an S8, and I've got another S8, and I've got another S8. These are molecules. What holds the molecules together? They are all nonpolar molecules, so they are held together by London forces. What type of crystal lattice would you be if you were made up of a molecule, another molecule, and another molecule? You would be a molecular lattice. Consider the following substances: carbon, sulfur, sodium, sodium chloride, and water. Which one is a solid at room temperature and is a good conductor of electricity and shiny? So you're hunting for a metal. The only metal in that list is sodium. A substance that has an allotrope, that is a giant molecule with an extremely high melting point, that is your diamond, but diamond's not there. So I look a little harder and I see that carbon is there, so A is correct. It does not conduct electricity, but it does become a good conductor when it melts. So I'm looking for something ionic. I'm not sure what. Let's see. Oh, only sodium chloride is there that is ionic, so that is D. And a substance in which hydrogen bonding exists, I'm looking for water. Oh, goody, it's there. So water, but I could have been looking for ammonia or hydrogen fluoride. Now we've got structures of different ionic lattices. Define an ionic lattice. It is an attraction between anions and cations. To form a lattice or whatever. Under which circumstances are these substances able to conduct electricity? It is when they are molten or melted or in solution. Why? Because the ions are free to move, not the electrons. The electrons are still bound in the ions. Ionic substances conduct electricity by ions, not by electrons. Suggest with a brief explanation which of these substances would have the higher melting point. It's going to be magnesium oxide, and the reason is magnesium and oxygen have got double the charge. Double charge, therefore more attraction, therefore difficult to melt. You could also have said to me they have a greater electronegativity difference and therefore would be a more polar attraction, and that would be more difficult to pull apart. Consider the diagram. What bonding is represented? That's your absolute classic picture of metallic bonding. Positive kernels and a sea of delocalized electrons. Now you have to choose a metal. Some of you chose the most obscure metals under the sun. You could have just told me copper or gold or silver, any metal. They're held together. You don't need two different metals to have this type of bonding. It's what holds metal lattices together of even one type of atom. This type of substance conducts electricity when in the solid phase. How is this possible? The delocalized electrons are free to move. Consider the methanol molecule, which has a molecular formula of that, and it's been given. Label the most polar bond. I had kind of broken something up for you here and made it a little bit clearer. I put the O over there and then put a line there for you to clearly show that that was a bond. And as a bond, it is the most polar between oxygen and hydrogen. So that was your label over there of the most polar bond. And then draw two methanol molecules. Now, when you put them in, you've got that there, and you know that the O is slightly negative and the oxygen is slightly positive because of the electronegativity difference. So when they pack together, the slightly negative, slightly positive need to be close to one another. So they're going to pack together like that. Here's the one molecule. Here's the other molecule. And what holds them together is this dipole here would be attracted to this dipole over here. So it is a dipole-dipole force. Dipole-dipole. Actually, it's not. It's really going to be a hydrogen bond force, but I haven't taught you that yet, and I'm only going to teach it to you when we do organic chemistry. So for the moment, I found it perfectly acceptable that you understood it as being a dipole-dipole intermolecular force. It's between two slightly positive and slightly negatives. This example was basically identical to what you had in your last test, and I was hoping that you would have spent some time in your last test going through your last test, and therefore this would all be very familiar to you. So we've got two oxygens. They ask you to use Cooper notation. So actually I really should have seen the Cooper notation. I didn't penalize you too much, but if I say use Cooper notation diagrams, then actually I need to see Cooper notation diagrams. And then the next thing that we're going to do is we're going to say how much energy is absorbed. And I have got 1, 2, 3, 4. 4 times 413, which is equal to 1652. And 2 times 1, 2, double bond O, 498. And that is equal to 996. I need to break those bonds, so I need to add that energy. That energy must be absorbed. Then, once I've absorbed it, I'm going to make new bonds, and I'm going to make 2 of the C double bond O, and I'm going to make 4 of the OHs, and I am going to then say that the amount of energy released is 3466 kilojoules. And then the net amount, the change, the heat of the reaction, the net amount released is going to be those two subtracted, 3466 minus 648, and I get 818 kilojoules released.